As Antonio was saying, I'm going to talk about some extreme photon sources that we're working on at CERN, and in particular, into two areas, in the gamma ray source production and also the X-ray source production. And they are based on the interaction of lasers with different types of particles. So in the introduction, we hear about synchrotrons, maybe FELs. They all work with electrons, but actually back at CERN, we have a new experiment that is based on the interaction of lasers with ions, with ultra-relativistic ions. And I'm going to talk a little bit about that because that's a relatively new idea. And there is still not a lot of experimental demonstration about it. And then in the last couple of minutes, I don't have a lot of time today, I will introduce the X-ray sources we're working on based on inverse content scattering, meaning ultra-fast lasers interacting with relativistic electron beams. So if we look at the high-energy photon spectrum in the X-rays and the gamma rays, we will find a lot of Compton sources, inverse content scattering sources, that they pair different types of accelerators, storage rings, linacs, energy recovery linacs, with ultra-fast lasers, and they can achieve photon fluxes in the range up to 10 to the 14 photons per second, depends on the photon energy quite a bit. So, and those, they're trying to compete with very well-established sources like the free electron lasers, that they achieve much higher photon fluxes up to 10 to the 16 photons per second, but at lower energies, lower energy range, let's say up to 10 to 20 keV. We're talking about here gamma rays up to 1 GeV photon energy, which is interesting for applications in nuclear physics or particle production, like muons, pions, etc., which CERN is interested in. So the first project we have, the Gamma Factory, it's actually aiming to increase not only the photon energy available from free electron lasers by a factor of 10 to the 4 from the 10 keV to close to the GeV, but also 10 to the 7 in this spectral range in terms of photon flux and up to 10 to the 16 photons per second. So the question we are addressing here is if we can make such a technological leap of 7 orders of magnitude to deliver similar fluxes to FELs, but in the gamma ray section of the spectrum. Just to put things in context, if we calculate how much is the energy of such a beam in terms of power, if we compare it to European XFEL, which is perhaps the most advanced FEL source in Europe, we're talking about comparing about 40 watts of X-ray light to half a megawatt of gamma ray light, just by changing the photon energy from 20 keV to 400 MeV and maintaining the fluxes similar. So if you want a source of light of 600 kilowatts of average power in the gamma rays, you naturally need megawatt class accelerators and megajoule store beam energies. And currently, there's only one facility in the world providing this type of beams, which is the Large Hadron Collider at CERN. So what is the interesting idea here? So the basic idea is to use the Doppler effect twice with ultra-relativistic ions. So we can think about it in the lab frame or in the ion frame. I think it's, I will jump from one to the other to try to make it as simple as possible. But in general, we will have an ion that has been removed many of the electrons, so it's a heavily stripped ion. And then it's colliding, counterpropagating with an infrared beam. And if this is close to the speed of light, obviously it will perceive and squeeze frequency, so it's a Doppler shifted frequency. And if we actually tune the ion speed to this squeeze frequency, we can access resonant transitions in the X-rays. And we can excite this ion resonantly in the X-ray directly using infrared light. Now, this excitation basically fluoresces or de-excites very, very fast. And this emission happens the same thing. So it's the emission from an ultra-relativistic ion, meaning that it will have another boost in the frequency by a factor of gamma, which is the speed of the ion. So you get this very similar to the Compton scattering for gamma square factor here, but playing with a transition. And this is the main trick, that actually, because this absorption process is linear, then the process is very, very efficient. So we try to, we're establishing now the experiment to prove this. And at CERN, we have a bunch of accelerators. The large one here is the Large Hadron Collider. It's very busy, so we cannot do our first experiment directly there. So we're doing a proof of principle experiment with a less energy beam in the superproton synchrotron, which is this other ring here that is only 7 kilometers long. And it has a very convenient area here with a laser room near adjacent to the accelerator to a straight section of the SPS. It's very close to the famous Atlas detector back here at CERN. And the experiment is going to look a little bit like this. We'll have lead ions, which were demonstrated in 2018 in this accelerator. And it will interact with 5 millijoule pulses of 3 picosecond infrared pulses. And 5 millijoules is enough to actually fully excite or have a saturated excitation of the ion bands. And the interesting thing here is that we have 5 millijoules, but the repetition rate of the ions is 40 megahertz. So if you compute the average power that we need for the laser, is 200 kilowatts. Now, 200 kilowatts, obviously, it's not available on the market. And the strategy that we chose is to actually install a Fabry-Perot enhancement cavity, and with a finesse of 10,000, and then rely on a much more affordable laser system that is only 100 watts and produce 2.5 microjoules pulses. And then we inject here, we amplify those pulses in the Fabry-Perot cavity, etc. Now, for a finesse of 10,000, the type of precision that one needs and reflectivity, it's very high. You need a frequency comb. You cannot use a standard mod-lock laser, obviously, because otherwise we wouldn't stack the pulses inside the cavity. And if you calculate the line width of this frequency comb, it needs to be less than 2 kilohertz. And then the mirrors, they need to be sort of a LIGO style. So this was quite a challenge. And then we contacted a few companies, and we ended up acquiring an ultra-low noise frequency comb from Menir Photonics. I think they will speak today later. So I say thanks for this laser. And now we're working on this also power amplifier to 100 watts with different vendors. And we expect to have this installed in the tunnel in the next few years. And after the interaction happens for the proof of principle experiment, we will have 40 keV photons at 10 to the 15 photons per second, which is already very comparable to the European XFEL. And this is a little bit of an update of the status of this project. We have tested this laser with a Fabry-Perot cavity that was installed in IJC lab in Paris that is used for Photonics, another X-ray experiment. And we already demonstrated above 500 kilowatts of average power of infrared light in a 35,000 enhancement cavity. So if you want to know more about this, please go to this paper and read it. It's actually a very exciting results, and we are actually working now in going close to the megawatt level of average power. Now, I'm gonna switch gears now in the last couple of minutes and tell you very, very fast about a more traditional way of generating X-rays by interacting laser pulses with electron beams. Electron accelerators, they're more commonly linear than circular. And we have a few of them at CERN, and they don't have a continuous temporal structure, meaning they have bursts of electron pulses, at very high repetition rate, at gigahertz repetition rate. And if we want to do the same idea of using an enhancement cavity, like a Fabry-Perot enhancement cavity like this one, to do a very similar experiment, to do Compton scattering, then the laser that you need is quite different. So because we can take advantage of the temporal structure that has bursts and basically charge this optical capacitor, that's how we call it sometimes, this Fabry-Perot cavity, with a burst or a train of pulses. And once it's reaching saturation, then we inject the burst of electrons. And then in this way, we have a little bit of a simpler and less stringent requirement laser for the Compton scattering. because the number of pulses requires here is proportional to the finesse. You can actually put a lower finesse cavity and have actually mirrors with lower reflectivity, etc. So the frequency comb required for this application, it's actually not as thin as with the Gamma Factory. And this is why we were thinking, we team up with a team in Bordeaux in LP2N to develop electro-optic frequency combs that they can work at gigahertz repetition rate, and they generate very efficiently bursts that they can be injected in Fabry-Perot cavities. So the principle behind, I cannot go really behind in detail in the principle, but it starts from a continuous wave stabilized laser, and then a series of modulators, amplitude and phase modulation, and then after compression, we obtain a programmable train of pulses. And this is really interesting for gigahertz repetition rate applications, because we can not only change the repetition rate, but also the pulse duration on demand. And this will be very, very handy once we do experiments with it. And we're actually building a prototype at CERN. And the idea is to use burst amplifiers that we had before and develop this new frequency combs, either electro-optic fully, and combine it with our old neodymium GELF amplifiers that they are still working, and they can reach very high burst energies of Joule-class burst energies, which will be ideal for this kind of application. So I hope it was not too busy, but I just wanted to conclude saying that there's a big interest in CERN in demonstrating these techniques, not only to produce the high photon energy beams, but actually that is the byproduct of cleaning up the particle beams. So in general, this is a useful technique with or without the high energy photons output that we get. We have on one hand the Gamma Factory, which is aiming to produce these 400 MeV photons, 10 to the 16 photons per second. And then we have this inverse content scattering X-ray source, which right now it's developed together with electro-optic frequency comb technology. And with this, I would like to thank all of our collaborators across Europe and the world, and you for your attention. Thank you very much.